So till now, if you see, we have been discussing with mostly mechanical systems. So to understand the basic vocabulary which we will be using for describing acoustic system. Now it will be quite faster because we will just be correlating things. We will say like in the spring mass damper system, this happens like this. Okay, so it will be faster now. At least we will try to make it. Um, but now once we get into the acoustic, we did up to string, right? So we didn't go to 2D things. So it was a 1D problem. We solved that. And then we are now going to acoustics. And if we directly jump into the 3D acoustics, it will be too much of generalization from that 1D string problem to complete acoustic problem. So what we will do, we will again take steps like we will see first 1D acoustic things, okay? And that 1D acoustic has another name. It is known as a thing called plane waves are propagating, okay? So the term is plane wave. That means anywhere in space, if you look at the wave, its direction is same. Okay. In the most generalized kind of acoustic waves, the directions will be different in different places. But for plane waves, which is the simplest one which we will start with, all the places the direction will be same. And in fact, the simplest way to visualize such conditions is to think that there is a tube and you have some sort of piston here and you are oscillating that piston like this. And because of this motion, a wave will be generated and propagated along this tube, and that wave will be very, very close to, means we can for our course we can even say that that will be completely a plane wave, okay. So that means waves will just move like that, and then that means any plane if you look at, those particles will not go to any other plane after some time. They will stay, they'll stick to their plane. Okay. So that is why the plane wave. And one more assumption which we will take up, and then that is true for the full course in fact, that all the values of pressure, the velocities, displacements, they are going to be very, very small. Okay. So that brings us to linear acoustics. So there will be no non-linear effect. The similar things which we did for the string also. That means anywhere the deflection was very small. So it's very similar. So we will stick to that kind of small values. Now how small is that small when I am saying pressures are small? Any idea in what range we are talking about? In fact, any guess? In fact, the pressures we are talking about, they are of the order of just some guess at least. Before I just tell the number. Okay. So we are talking in terms of micropascals. Okay. So the reference value means with respect to that value we speak everything, all the pressures which we will be dealing with. So that reference pressure is actually 20 micropascals. How much is 1 Pascal, by the way? Do you have a feeling about 1 Pascal? I mean, how do you feel 1 Pascal? Because we have a feeling about, say, 98 degree Fahrenheit, right? So 1 centimeter we have a feeling. So like that 1 Pascal, how much do you think? Yeah, Acha, did I tell that sometime, or yeah, anyway. So almost like 1 apple on a 1 meter square area. So the pressure which you feel that is like 1 Pascal, and we are talking about you cut that apple into 1 lakh pieces, and 1 piece you take and put that on that 1 meter square area, and the pressure now you feel is that pressure which we are talking about, this 20 micropascal. And what about the atmospheric pressure? How many apples? 1 lakh apple actually. Okay, so that's the scale in which we are talking about, and the power which generally we talk about in um, uh, 10 to the power minus 12 watts. So in that range of power we will be discussing about. We will see how and what that means. But this is the general idea. So when I say small values, so these are the values which I am talking about. Okay. Okay. So having discussed that, one more point which we need to discuss. See, in any literature of acoustics, they will use the word particle. Okay, now air particle like that. Now never you should assume that it's a molecule, because students always get a feeling that whenever they say particle they think that it's a molecule. It's not a molecule, it's about a small volume of a chunk of air. Now again, how small that chunk should be, it depends on how closely the particles are distributed. In the sense, the mean free path should be used to talk about with respect to that how small this volume is. Okay, if you go below that, then you will hardly find any molecule, and you can't write even differential equations there, because the assumption of continuity of a function doesn't exist below that. So you have to go to only that level of small volumes where still you can use the concepts of continuity of a function. Okay, because what happens is sometimes suppose you go to very high altitudes, and if you try to use the same equation which we will derive now, if you want to use that, it won't work, because the differential equation itself, we will derive it in terms of differential equation, and it won't work there, because the distances are so huge before any molecule sees another molecule. I am talking about very high altitudes. Okay. So that's a very important thing. You have to shrink to a volume which is very small, but it is not that small that only 1 or 2 molecules are there. Okay. So that is one thing, and then why do you think in a qualitative way, when do you think a sound wave starts propagating, or we call that as a sound wave or something? It requires and then that is very closely related to this how how densely packed these particles are. Okay, for example, see, suppose there is a room here, okay, and there are people in that room dispersed like that, and suppose you have now a table somewhat like this, and someone wanted to do some mischief, and he pushed this table. okay, certain distance. Now, do you think that anything bad will happen, because they are quite in a way sparsely dispersed, right, people. So some people will get affected by this movement of the table. This table will be moved, suppose, okay, and they will adjust themselves. After a certain time they will adjust, and these people may not even know that something happened. But now if you just imagine that the room is completely filled with people with very less distance between them, and now you imagine the same thing happens, then they will now pass on this information, in the sense they will fall on each other, and that effect of push will move along people. So now that depended on two things. One is how close these people were to each other, and how much distance you moved it. In fact, one more thing, how fast you did that. Because if you move the table very slowly, then also they will get time to adjust. So they will not. Now all these things are related to all those three concepts, right? Inertia and what? Stiffness and damping. And mostly in this course now onwards, damping will not be considered, because in air we will be discussing mostly. And the damping property of air for acoustic wave is very, very low. For our consideration, it won't be there. So mostly our system will depend on the mass or the inertia and the stiffness. So here, so that's what is the inertia and the stiffness will decide how far and how fast should we move so that a disturbance should propagate. So very similar thing happens in also in acoustic. For example, see, they say that when you clap, you hear a sound. Now, why do you hear a sound? Because of what? A pressure wave, a higher pressure builds up, or what? Means there is a normal atmospheric pressure. Over that, some pressure is building up because we are clapping. So, what do you think? This pressure is a higher value than the atmospheric pressure which you are listening? Actually, not. Otherwise, what would happen is, if you just bring your hands together, still a higher pressure is getting generated. You can feel it if you do like this in near your face. No, you can feel the pressure. The air actually is coming to you, but you are not hearing any sound. You are hearing the sound when you just touch it. Why so? Because this fastness comes into picture. That stopping is the thing which caused it. You were bringing your hands closer, so air was trying to get out of this system, but then suddenly you stopped it. That's what created a sort of, they had inertia. They can't stop immediately because they had mass. So they will move. As soon as they move, move means those people who were actually trying to move when you are bringing it together. So they will move somewhat distance. So that is why a low pressure zone will be created, and that is what we are hearing as sound when we clap, and not the high pressure which is getting created. So that's what is this. So this speed at which you are doing this change is a matter of importance. So that is what so three things: density, amplitude, and speed at which you are doing that. Okay, these three things will in general play crucial role in deciding about what sort of sound is getting created, how large a sound is getting created, what are the frequencies. All those things will be based on these aspects of the system. Okay, so yeah, with that qualitative introduction, now we can go and see how exactly we will derive the equation which governs the movement or the motion of the wave, which we call the acoustic wave.